Hi everyone, this mix is going to go through transmission diffraction gratings part 2, and it's going to be looking at what the number of maximums are when we're looking at a transmission diffraction grating interference pattern. It also has a look at how white light can be diffracted and the properties of diffraction gratings that make them really useful in spectroscopy. Okay, in terms of our outcomes, we're actually looking in this mix at the last 5 of these outcomes here. So looking at the number of order of maximums possible, how come there are areas of dark in between our maxima, and how we are able to utilize, I guess, this formula and diffraction gratings, and what happens with white light, and also, yeah, as I mentioned before, the properties that make it useful for something called spectroscopy. Okay, so just to recap, when we use a transmission diffraction grating, we observe a particular pattern, and it's similar to our Young's double slit interference pattern, but it shares some common features. So we're using the formula that we've derived in the previous mix, which is d sine theta is equal to m multiplied by lambda. Now d is the distance between the slits, which for a diffraction grating it should be very, 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 very small. Lambda is the angle from the normal, the viewing angle, I guess, to the particular part that we're looking at on the screen. The m is an integer depending on whether it is a constructive or a destructive part of the pattern, and lambda is the wavelength of the light. So a number of bright reinforcement lines will be seen on the screen, and these are referred to as orders. So there'll be a central one and then a number of orders of maxima as we move away from that center. Okay, so when we look at a diffraction grating interference pattern, it looks similar to what we've got on the screen down the bottom here, but you'll notice straight away that this diagram is obviously not to scale. In the middle we have what's called the zeroth order maximum, or the central maxima, and then as we move away from that, there will be the first order maxima and second order, third, fourth, and so on, either side of that central one. Now, what you will probably, well, hopefully would have picked up on, that this diagram isn't to scale, because as we move away from the center, the distance between those fringes should get progressively larger. Now, some of the things we have to remember is the spacing of the slits on the grating actually determines how many orders of the diffraction pattern are seen. Now, it might be 2, it might be 4, it could be 7, and it really depends on the number of slits on our diffraction grating and what sort of light we're actually using. And the reason for that is that light cannot diffract past 90 degrees. So the maximum value of m, or how many orders there are, will actually correspond with an angle that's either equal to or less than 90 degrees, because we can't actually see what happens past 90 degrees. If we're given a picture of an interference pattern, we can actually work out the maximum number of orders, because it's equal to the number of maxima visible on only one side of the central. So it doesn't include the 0 order maxima, and it doesn't equal the total number of visible maxima. So if we have a look at this diagram down the bottom, if this was the picture that we were given and we were asked to find out what is the total number of maxima possible, then we'd see the 0 one doesn't count, and we're looking at one side only, so we've only got 1 and 2. So there would only be 2 orders of maxima visible for that particular source of light. Okay, so we know that a diffraction grating interference pattern is slightly different to that of the Young's double slit experiment, in that there'll be a center, and next to that there'll be one that's a little bit less bright but a bit further away, and so on and so forth. So they'll get more faded or less intense and further away from each other as we get further away from the middle. And one of the things we're asked to do is explain the regions of negligible intensity between the intense peaks. So why are there areas of annulment in between these order of maxima? And the reason for that is that a diffraction grating contains a large number of slits, and that means that while the waves from adjacent slits are only just out of phase, because there's hundreds and hundreds of slits available, one that could be 100 slits apart might actually be half a wavelength out of phase with that particular wave, and then they might annul completely. So it's possible that all of the waves, or almost all of the waves from the diffraction grating, might pair up like that and produce complete or almost complete annulment for the most part. So unlike a two-slit diffraction grating, there is much more complete destructive interference between maxima. And so hence why the further we go out, the more, or the broader the areas of annulment actually become before we reach another section of two lucky waves perhaps that have actually coincided and reinforced each other. Okay, so the one of the other things we have to look at is white light pattern from a diffraction grating, or what actually happens if we shine white light onto a diffraction grating. So when we do that, we'll see a central maxima, which will be white, as every colour will reinforce at the centre of the screen. So if we look at our formula, d sine theta when we're looking at 90 degrees is going to equal 1, so it's going to be 0, which means that there's going to be no path difference, and if there's no path difference, then they're all going to be reinforcing each other. So that means that all of the wavelengths, regardless of their actual length, will reinforce each other at that central point. So hence there'll be a white band, and then to the side of that there'll be an annulment area or dark patch on either side of the central maximum. And following this area, there'll be a continuous spectrum of colours. So the colours will actually start to separate out depending on their wavelength. And the colours will range from violet, which has the smallest wavelength, so it will be diffracted the least, and it'll be closest to the centre maximum, and then it'll spread out to red. Now after that we'll see another section of annulment, and it'll spread out even further in the next spectrum and further. Now higher order spectrum, so beyond the first one, are also formed further away from the centre. Now they'll be fainter and more spread out, as I just said, and after about 3 orders the spectra of adjacent orders will start to overlap. So if this little diagram was extended 1 order further, we would see that the colours of the next one, which was so spread out, that actually start to overlap, and we might not get into like a patch of black in between the two spectra, and the colours would start to blend together. So what that actually looks like in diagrammatic form is if we have our white light coming in this side, and it hits our diffraction grating, and we're only looking at the half of the diagram essentially, but this same diagram will be repeated underneath. So we've got our white central maxima, and then it would start to spread out. So here we've only sort of got red and blue, but it would be an entire spectrum, so from red all the way through, not just to blue but to violet. And so we have our first order spectrum here and our second order spectrum. So red has the largest wavelength, and so that has the largest angle for its maxima. So the angle coincides with the size of the wavelength. Okay, so lastly, we're going to look at the properties of a grating that is useful in spectroscopy. Now, a spectroscope is a telescope kind of device that uses a diffraction grating to separate out the colours or the maxima, and you can measure the wavelength. So the properties of diffraction gratings that make them useful for this is that wavelengths can be measured accurately by using a diffraction grating in a spectroscope because of the specificity of the measuring device of the angle. A diffraction grating is also able to separate wavelengths, different wavelengths of light. So because a diffraction grating will separate different colours or different lengths of wavelength really well, it's able to be used to identify particular atoms or molecules that produce discrete line spectra or absorption spectra. And lastly, a diffraction grating will produce a more dispersed spectrum and also a clearer spectrum than a triangular prism, which was how colours were usually separated out into a spectrum. So those 3 points there are what make diffraction gratings really useful in spectroscopies.